And welcome back everybody to Unit 2 Forces. Alright, this is video number 3, as you can see. uh, we've got a lot to do with tension. So we're going to start off by just kind of introducing the force of tension, and then we're going to start to look at what to do with two or more forces of tension, and then Atwood machines, which kind of take tension in a new direction a little bit. And then we're going to work on tension at an angle, which is a lot more complicated. So starting off with number 1, tension has to do with ropes. It's every time there's a rope in a problem, you'll have the force of tension. Unlike normal force, which is always with a surface, the force of tension will always pull. So if you have a rope and you're pulling something, you can't push something with a rope. So if we have a rope with an object attached to it, right, hanging from this little dot or whatever, this object has 98 newtons, and if you didn't know how we got that, I don't know, go back to one of the other videos. That's just 10 kilograms times 9.8 meters per second squared. And just like the normal force, actually, when there's only one rope pulling it up, it has to equal the force of gravity. So when you have the force of gravity pulling it down with 98 newtons, in order to stay still, it has to be pulled back up with 98 newtons. And that's really all there is to it with tension. Until you start pulling stuff harder. So now this example is when the rope has more tension than there is the force of gravity. And the only difference here is that instead of just staying still, this object will now be pushed up, accelerating up with a force of 49 newtons. And that's about it. I mean, like, if you want to find the acceleration, right, you cover up A, you get net force over mass, 4.9 meters per second squared, and that'll be going up. So instead of saying still, this is probably moving up too, because if you just have a rope with the same length all the time, then you have to be pulling this up with 4.9 meters per second squared. And the same would actually be true if there's not enough tension in the rope. If there's not enough tension in the rope, then it'll start going down with something proportional to the force of gravity. Alright, and then with two or more forces of tension, it gets a little bit harder, but really, if you just kind of use your head, you can figure it out. So we have the net force, it's a stationary object, so 0 meters per second squared, 0 newtons for the net force, which means that if we add F of T1, force T2, force of gravity, and these, you might see the force of tension or just a T. That's what I'll be using later, is just a T. But if you have T1 plus T2, and again, minus Fg because it's going down. Normally you would just kind of add up all the forces, but because it's going down, then we can move it over and say both of these, you go up, and then you have to go down the same amount. So if they're the same, if they each go up halfway, then each one is 49 newtons. And Atwood machines take tension in a little bit of a different direction. So, and when you're learning new things, it's good for your learning just to kind of like test things out and test edge cases. So the idea of an Atwood machine is that you have two objects and they're being connected by a rope. So this is just a single rope all the way around this pulley, and there's no friction. So in a real one, you would probably use, like, I don't know, WD-40 just to kind of like grease it up. And that would prevent, the rope from just like staying still. However, when the two objects are the same mass, have the same gravity, then nothing happens. They just kind of stay still, right? because if this one is being pulled down with 10 times 9.8, 98 newtons, right? And this one has 98 newtons. They're both, I mean, like, nothing's going to happen if you pull up and push down at the same force, nothing happens. Although something will happen when we have 15 kilograms, which will have more gravitational force, as you can see when this arrow got longer, right? A good way to visualize an Atwood machine, just kind of in your head, like, they're always symbolized with these pulleys and stuff, but because it's just one rope, you can draw just one rope in between them. So if you have this rope with two objects, then you keep the forces. So now this one is being pulled to the left and this one is being pulled to the right. And I'm going to say that right is going to be the positive direction, even though when you put it back on the pulley, they're both pointing down. So it takes a little bit of a jump here to go from this to this, but if you just kind of think of it as one rope without a pulley, then the idea that, you know, this going up is positive, but this going down is positive too. It's because when you connect them in just a straight line, right is the positive direction, right? So if you have 147 newtons, 98 newtons, total force, the net force of the whole system is going to be 49 newtons. And that's going to be down this way and up this way, right? But then you can just use A equals force over mass, net force. But this is something to look out for. So normally, if I was looking at this, I might say, okay, so it's 49 newtons divided by 15 kilograms. But actually, this 49 newtons is applied across the whole thing, the whole system. So not only is it moving this 15 kilogram object, it's moving both this and the 10 kilogram. So, right, this force, this tension, is moving this whole system along. So it's moving 25 kilograms. And if you just kind of plug that in, you get 1.986 meters per second squared. And that'll be, again, this side of the rope is going down, this side of the rope is going up, because you have the same length total, right? If this side gets longer, this side has to get shorter to match it. So the acceleration is the same across the whole system. And this actually really tripped me up, because I had to go online, I had to find how to do this, and it went through so many different ways to find this acceleration with this massive formula. But all it is the net force divided by the total mass. Like, that's all it is. We already did force over mass when we were looking at the triangle, and now we just have net force, total mass. It's actually not that bad. Although it does start to get bad when we look at angles. And this one should be fine, but the next one is going to be really tricky. So when we have two tensions, but instead of pulling straight up, now they're pulling at an angle. And it'll go through a similar process to when we were just going straight up, just one extra step for this one. So we start with just adding them up. So we can add up the oranges and then the purple and then the red, right? The red is the Y component. So each one goes up a certain amount and each of those have to cancel with the purple. But also the X directions have to cancel, because if this one's going left, then this one has to go right the same amount to, you know, cancel and go back to 0 here. And so just like the one where they were just going straight up, the Y direction, these red parts, are both 49 newtons. They're both half of the gravity. However, that's only the Y direction. We don't have Y in this free body diagram. We have orange. We have tension, not the Y direction of tension. And to find this, we're going to need trig. because we have the sine of this angle here, and I measured it with a protractor actually. It's 43 degrees, which I'm sorry, it's really random, but we have the sine of 43 degrees is the y over the hypotenuse, the opposite side over the hypotenuse, which in this case is red over orange. And I'm just going to keep these here as colors just to try to keep you along with it, right? And if we're trying to find the tension force, then you just multiply it across, dividing by the sine. So that's something that trips me up a lot, is when I forget to divide by sine, and I just say that it's red times sine. But if you use the triangle here, right, if you're trying to find the hypotenuse, which is the longer side, you cover it up and you have opposite over the sine. You have the red over the sine. And we already found red was 49 newtons because it's half of gravity. So, like I just said, 49 newtons divided by the sine of 43 degrees, and you get 71.85 newtons. Now, this should make kind of a little bit of sense. Visually, these, right, should be 72 newtons. This is 98 newtons. So these should be about 3/4 of this length, which kind of checks out. And that's like the whole hypotenuse. The vertical part is only halfway. But it gets a little more confusing with this. And I already did, so these are actually to scale, as you can see here. And this was just a bunch of different ways to view all the adding of the vectors. So for this one, I just added the two tensions. And then this one, I added the vertical components and the gravity. And this one, I just straight up, this is the sum of the forces. So this is T1, T2, and force of gravity. So this is indeed a stationary object, right? The sum of all the forces is 0, it comes back. And these are going to point to some special things that we're going to work on. So the x directions, the greens, are going to cancel. These two have to be the same because there's no other x direction forces. And I drew this dotted line to show you like where the angle is. So the angle is between the horizontal here and the force of tension and the string here. And same thing with this one. So this one's a lot bigger at 60 degrees. This one's only 20. And then the force of gravity as normal is just 98 newtons. And we can get started on this. And I got a little lazy with the animations because this is a lot of vectors. And it's a lot of math. So prepare yourself. So when we get started, we're going to work with the x directions first because we know they're equal, right? The green sections were equal. So we're going to start with the x directions first. So we have t1x and we have this little triangle here, right? This is, pretend this is cosine just for a second. And then we have, you know, if we're trying to find the adjacent side, then we have cosine times the hypotenuse, which is t1, cosine of 20 degrees. And same thing for this one. Right, this is t1 times sine of 20, because it's opposite over hypotenuse. Same thing, you just multiply it or use the triangle or whatever. Alright, and then I am going to follow along after each step. I'm going to have some just decimal equivalents, because I know that sometimes all these sine and cosine ratios kind of trip people up, right? It gets very cloudy, and like it fills up your paper very quickly. So after each step, I follow along with a 4 decimal place equivalent, and I'm using 4 just to kind of minimize the rounding error, because you know that was it gets a little rough if you only use 3. Alright, next step for T2, it's the same thing, right? If you have cosine of 60 degrees is adjacent over hypotenuse, then you just multiply the hypotenuse and you have T2x, T2 times cosine. Same thing for the sine. And then this works out to 0.5 and 0.866. And then, so now that we have these x direction forces, we can use the net force equation to show that they're equal to each other. So t1x plus t2x plus fgx, which is, you won't really see this very often because it cancels, right? This just becomes 0 because it's only vertical. There is no x direction to gravity. It's just straight down. It's not like the normal force with the inclined planes or anything, because it's just straight down. We're not breaking it into any new components or anything. And then I also put that t1 is going left, so I put it as negative. And then it's all equal to 0, just so that, you know, it's not moving, it's stationary. We saw that when we added up the vectors. And then when we start with negative t1x equals t2x, then we show that the x components are equal. And then, as we showed before, we just kind of substitute t2x for t2 times cosine 60. And t1x is t1 times cosine 20. And if you actually want to follow along, that's probably a good idea, because I'm only showing the steps that we're on, not necessarily all the stuff that we worked on before. So like this was from the first step that we just did. Right, and then we just divide by cosine of 60 to get cosine 20 over cosine 60 times t1. So this is t2 in terms of t1, right? And it's a little confusing, but we'll use this in just a second. We don't actually know t2 yet. We just know in terms of t1. Right, and then so now that we have all the x directions and stuff, now we can work with the y direction. And we have t1y, t2y, minus fg. I skipped a step here. Instead of simplifying after a step, I just did that right away. Because it's going down, I put a negative. We add them together. These were the red sections that added up to get fg. And remember, if you can recall, right, t1, because it's at that 20-degree angle, this y will actually be a lot smaller than the t2y. So we start with, we had the sum equals fg, and then some substitution. And don't freak out for a second, just bear with me here. So we have t1y equals t1 times sine 20, and again that was like the second step we did. And then t2y is, and this is t2 times sine of 60. We already had that t2y is t2 times sine of 60, but we just found in the previous step that t2 equals t1 times all this, or that constant, it was like 1.8 or something, times t1. All right, so this is t2 times sine of 60, or t2y, right? And that's why it was important to find in terms of t1, because now we can factor out a t1. So when you factor out, you divide each term by the thing you took out. So we're taking out t1, so each term, right? Now this t1 cancels, and then this one, we take out the t1. And then we have sine 20, cosine 60 times sine of 60. And I left it as a fraction here just to show you that we are multiplying it. That's what these parentheses mean, right? It's just multiplying. And then now we have t1 times some big, all this is just a big constant, right? Sine of an angle, cosines of angles, they're all just numbers. So we divide by all this to get t1. And I plugged in f of g is 98 newtons. And then instead of rewriting this whole big thing underneath the denominator here, I just rewrote it as about this. And then we move in, simplify. Now we just have T1, 98 over all this stuff is 49.756 newtons. And this was using just the decimal equivalents. So I just did sine of 20, rounded to 4, and just kept going with that. And we got a little bit off. So this was 5.6, 5.6. This was 5.7. That's a tiny amount. That's 1,000th of a newton. It won't really affect a really big number, like 15 kilograms or anything like that, right? But you can notice T1 was the smaller one, and the orange part, the whole value for T1, is about half of Fg, right? Half of Fg is 49 newtons, and this is 49.7. So it's just a hair bigger than half of Fg, which I thought was interesting. But that, that has nothing to do with the actual problem. That's just something cool that happened. And now we're almost done. This is the last step. Now we have T2 in terms of T1. We have T1, and all we got to do is plug it in. So if we have T1, we just multiply by this factor, cosine 20 over cosine 60, to get T2 is 93.511 newtons. And again, with the decimal equivalents, this one was just a little bit bigger at 514. This was 511. But again, a couple thousandths of a newton won't affect any experiments or anything. So if you don't like the cosines, just make sure to round to like 4 or 5 decimal places to get rid of the rounding errors. So now if we go all the way back to this, we found that T2 was like 93 newtons and this one was like 49 newtons. So that checks out. This one's a lot bigger, this one's a lot smaller, and we already showed that these two both add up and it all works out, right?